So for this video, we're going to learn how to find the volumes of revolutions using the disk and washer method. To start with, let's see what a graph looks like when it's rotated. So, we'll take the equation y equals x squared. Now, as we all know, the graph of y equals x squared is going to look something like this. Now, right now I'm only drawing it from 0 to 2. You'll see why a little bit later. But what is this graph going to look like when it's rotated? Well, we're going to rotate it over the x-axis, which is right here. So when we rotate it, it is going to look something like this. And when you make that and turn that into a solid, it's going to have this kind of funnel shape. Now you might be thinking, how do I find the volume of this? It's not like we have a formula to find the volume of a funnel. So as it turns out, we can take this solid, and we're going to try to divide it into stuff that we can take the volume of. So for this, it turns out that this can all be divided into little tiny cylinders. So pretend that this is a cylinder inside here. And it's kind of a cylinder kind of rotated. So here's little cylinders, and there's going to be an infinite number of these. We're just going to draw one for right now. So now all we have to do is find the volume of every individual cylinder and add them up. So this might sound like a long and boring project, not to mention impossible, because in reality there's actually like an infinite number of cylinders in there, but it's actually pretty simple when we do it using integrals. So the first step to writing this integral is to, for the solid, is to write the equation of a cylinder. And as we all should know, the equation of a cylinder is going to be pi times the radius squared times the height. So this is actually going to be what goes inside our integral. We just got to do some changing things around here. So first we'll write the integral symbol. And then pi is just a constant, so that can just drop right down from our equation into the integral. So now all it's left to do is find the radius that we're plugging into this integral and then the height. So for this parabola, it turns out that each cylinder, the radius of that is just equal to the equation of the parabola, because here's the parabola part, and the half of the distance from the diameter, which is this whole cylinder, half of that is going to be from this x-axis right to the parabola, which is just the equation. So we're going to plug in x squared as r. And then in our volume equation, r is squared. So we're going to have to take that and then square it again. So it's going to be x squared squared. So now we just have to find the height. So what would the height of this cylinder be? Well, it's going to be this distance right here. So pretend that here's the cylinder. I'll draw a rotated cylinder over here for it. So we said that this is the radius, which was the equation of the parabola. So if this is flipped upside down, this is the height. So when this is rotated, it turns out to be this distance. And this distance is actually dx, because it's the change in the x value on this parabola. And dx always goes at the end of an integral. So that's going to be our final integral. So all it's left to do is just find the limits of integration for this. So what would it be? Well, it's going to be the starting and ending x values of this solid. And like I said earlier, I drew this graph from 0 to 2. So those are simply going to be our limits of integration, is 0 to 2. Now we could always solve this by hand, but to save time we'll just use a calculator. So when you type this integral into a calculator, your final answer is going to be 32 pi over 5, or if you want a decimal approximation of that, that's equal to about 20.1 cubic units, and those are going to be our final answers for this integral. Now, to continue with the disk method, we're going to try a problem that might be a little bit trickier. And this is going to be because this problem is going to be in terms of dy instead of dx. So, the problem is to find the volume of the solid that is enclosed by the line y equals 4x, and x equals 0, and y equals 0. So, let's start by making a sketch of the graph, which I started to do already. So here is the line y equals 4x, and then it is bounded by x equals 0, which is the y-axis, and y equals 0, which is the x-axis. So, what's this graph going to look, and we're going to rotate about the y-axis. So, it's going to look something like this. And when this becomes a solid, it's going to look like a cone. Okay, so now, the reason that this is going to be in terms of dy instead of dx is, if you notice, when we divide this into cylinders, the cylinders are going to go this way instead of vertical like in our previous problem. So, where before, the height of each cylinder was the change in x, well here, the change in the height of this cylinder is actually going to be dy. It's the change in y. Okay, so that means that our entire integral is going to have to be in terms of y instead of x. So our first step to make an integral in this is to change the equation of this line and solve it for x so that it is in terms of y. So let's start by doing that. So right now we have y equals 4 minus x. So let's solve for x. So we minus 4 from both sides. So then we get y minus 4 equals negative x. And then because the x is negative, then we have to multiply both sides by negative 1. Okay, and then we are left with x equals, it's going to be positive 4 minus y. Okay, so that is going to be our new equation, and from here on out we're going to use this in our integral instead of the original y equals 4 minus x. So like before, we are going to use the equation for the volume of a cylinder to determine what goes in our integral, and the volume of a cylinder is going to be the v equals pi r squared h. Okay, so now we have to determine what's going to go in for r and h, although we already determined h. So, in our integral, okay, so pi can just drop right down, just like before, because it's a constant. And then, just like before, the radius of this is actually just going to be the equation of the line, because here's the diameter of the cylinder, and half of that is going to be just this, the y-axis to the line. So we're just going to plug, but we're going to have to plug in the x version of the equation, because it's all going to be in terms of y. So we're going to put in 4 minus y, and the radius has to be squared, so we're going to square it. And then we just have to put in the height, which is going to be dy in this case. Okay, so now we just have to determine the limits of integration. Well, before they were the x values, where the solid started and ended. Here they're going to have to be the y values. So, in this case, the y value of where the solid starts is going to be 0, because it starts right here at the origin. So that's going to be 0. And then the top is going to be 4, because that is where this line crosses the y-axis to show the solid ending. So, and the y-intercept is 0, 4. So there's the upper limit. So now we can just plug this into our calculator, and when we do, we get the answer of 64 pi over 3. So that is going to be our final answer for the volume of this solid. And that's going to be our last one working with the disk method. Next we're going to work with the washer method. Okay, so let's move on to the washer method. Now if you've ever seen a washer, you know that there's a hole in the middle of it. And that's why this method is going to be used to find the volume of solids that have a hollow center. So let me use area first to explain how this method works. So right here I'm going to have a circle inside of another circle. Okay, so if I wanted to find the area of the big circle, I could do that easily as long as I know the radius. Or if I wanted to find the area of the middle circle, I could do that easily too. But what happens when I would want to try to find this area of this portion here? The part that is inside this bigger circle, but not including the little circle inside. So, what I would have to do is I would have to find the area of the small circle and subtract it from the area of the big circle, and that would leave us with the area of this leftover portion. So, we're going to use that same strategy when finding the volume of a washer-shaped solid. So, the formula for finding the volume of a solid with a hollowed out center is going to be this. The integral of two constants times pi, or of pi, big R squared of x minus little r squared of x times dx. Okay, so A and B is going to be where the solid begins and ends, and everything in the integral comes from the same cylinder volume formula we've been using earlier, which, as you recall, is pi r squared h. The only difference is we have to subtract the two radii of the cylinder, and that's where this big R squared minus little r squared comes from. So let's apply this to a problem. Okay, so the problem is to find the volume of the region enclosing y equals x squared plus x equals 0, y equals 0, and x equals 2 when it's rotated about the line y equals 6. So I started drawing a sketch of this graph, okay, and so this parabola here, that's going to be what x squared plus x looks like. And y equals 0 is the x-axis, and that's one of our borders for the solid, and x equals 2 is going to be right around here. So there's going to be another one of our borders for the solid. Okay, so this right here is going to be the region that's rotated. Right there, okay. And it's going to be rotated about the line y equals 6, which we know is a horizontal line. Now, if we plug in 2 as x for this equation right here, then we end up getting 6. So there is a point 2, 6 on this graph, which means that on this line x equals 2, y equals 6 is going to intersect the parabola at that same place. So we know that y equals 6 is going to be right here, crossing this point right here. Okay, so if this portion is rotated about this line, it's going to look something like this. Okay, and so we can see that when we make this a solid, it's going to be another cylinder-like shape, but there's going to be a hole in the middle of it. So our job right now is going to be to find the volume of this portion, not including this big hollow center in it. Okay, so let's begin by finding our limits of integration. So if this solid is bounded by x equals 0, which is the y-axis, and then this x equals 2 line, then those are simply going to be our limits of integration. And this is going to be another dx problem, just like the first one we did, because every cylinder in here is going to be, once again, going vertical. So dx is going to be the height. So there's going to be our limits of integration. And we know that from the volume of a cylinder formula that inside the integral there's a pi, like there always is. And the height of each cylinder, again, is going to be dx, because let's say this is a cylinder, dx is going to be the height. So we're going to have dx at the end of our problem. Okay, so now we need to find the radius, and that's going to go in there, and then we can just solve for the integral. So what we're really interested in is find the volume of this shaded area here, and just like in the circle we did earlier with the area of that. So we're going to have to take the volume of the whole solid, including this hole in the middle, and then subtract the volume of the hole. And that's going to leave us with the volume of this part that we are trying to find for. Okay, but as it turns out, we only need to subtract the radii, because everything else in this formula is going to be the same. So in this case, the radius of the outer solid, the entire thing, is simply going to be 6, because this line y equals 6, it divides the solid in half. Therefore, the distance between this end of the solid right to the center is just 6, which I wrote in there. So now we just have to find the radius of the hole, because this is going to be what we subtract from this radius. So this portion right here, it's also divided in half by 6, but it ends on this parabola, which is x squared plus x. So that means that the radius, which is this portion right here, is actually going to be equal to 6 minus the equation of this parabola. So that radius, we're going to call little r, is going to be 6 minus in the equation of the parabola, which is x squared plus x. Okay, so now that we have the and then when we can simplify this by distributing that negative sign, so it can actually simplify to 6 minus x squared minus x. Okay, so now that we have both of the radius of the outside and the inside, we can go back to that formula I showed you earlier with the big R and the little r. I'll rewrite it up here for you. So remember, it was the integral of a to b of pi and then big R squared of x minus little r squared of x and dx. So that's going to be our equation. So like we said earlier, 6 is the radius of this bigger, is the radius of the whole entire portion. So we're going to plug this in for the big R in this equation. And because in this equation both the radius are squared, so we're going to plug in 6 squared for big R. And then little r is going to be the radius of that whole portion that we're going to subtract it from. So then we're going to plug in this 6 minus x squared minus x as little r. So we're going to plug that in like this. So it's going to be the 6 squared minus the 6 minus x squared. I should have left myself more room. Minus x. And that whole thing is going to be squared. And then dx, like we said, is going to be the height of each cylinder. Okay, and now all that's left to do is just type this integral into our calculator, because this is going to be the final integral. So when we put that into a calculator, we get the answer of 584 pi over 15. So our final volume of this washer-shaped solid is going to be 584 pi over 15. And that concludes this video. I hope this has helped you understand how to apply the disc and washer method to finding volume.